Well, hello. We are off and rolling on chapter 7. This is all about counting, and you never you never knew counting could be so interesting. Hey, the first 3 sections I could easily skip and say, hey, you'll get it. But if you don't focus on the basics, when the things get a little squirrely, you just kind of have to go back to your basics and kind of say, what am I doing at each step? So I don't mean to waste your time here, but it's important to start out counting correctly. Here we go. So first thing you might run into is if you have successive choices, and if you have M choices the first time, N choices the second time, and P choices the third time, how many different ways can you go about fulfilling all these choices? Well, it is M times N times P. It is that simple, but that doesn't make a lot of sense. So let's do a quick example. All right, you are at Pooter High School. You are loving Pooter High School. You are loving Pooter High School, PHS. It is lunchtime. You need some money, so you're going to have to go home. You got to get some gas. And of course, oh, what is the name of that fancy wrapper that's got like a cheeseburger thing at McDonald's? So some kind of extra cool burger thing. So anyways, how many choices do you have to get from PHS to your house? Well, it looks like 3, and it looks like the one in the middle is like dodging through yards and all that. So we would say we have 3 choices. We can drive from our house and take, the road back here to Taft and down or around to Elizabeth. So we're going to say we have 2 here. And then, of course, when you can go straight down Elizabeth, boring. You can go down Elizabeth and turn right. There is our second geometry and construction house. A gal lives right here next to the church. Carolyn's her name. She's awesome. I'm sure you could stop by and say hi. Or, man, I'm just going to cruise down to Prospect, back, Shields. So there are 3 choices here. So ladies and gentlemen, if this was you and you asked how many ways could I drive from PHS to McDonald's, but I have to stop here and here, there are 3 times 2 times 3, which is 18 different ways. Oh, amazing. But it all comes down to choices, the number of choices at each iteration. All right, speaking of choices, maybe you go to a restaurant and you get 1 entree, 1 main course, 1 dessert. How many days would you have to go to get all the different arrangements of food? So you have 2 choices, you have 5 choices, and you have 3 choices. So you have 30 different menus that you could get. So good, so lucky. Oh man, let's see, what would I get? The bruschetta you got to go with, unless it's like ooh, man, creamy tomato. No, not creamy tomato. What is that? Oh, I forget what it's called. I'll go with that. I love good risotto, maybe with some scallops. And man, I'd probably chocolate mousse. I think the chocolate mousse would go with the risotto. That's what I would get. All right. Factorial, hey, we're already the first 3 sections. We're in the 3rd section here. Factorial notation, feeling pretty good. This doesn't mean you scream out n. It means whatever number that is. So 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And that is a number. Awesome. So maybe you look at this as representing choices that you may have at each successive. Ooh, that plays in nicely. All right. Some things that I have found that we take for granted is that, hey, if you have 7 factorial, you need to know that you can manipulate this any way you want. You could write that as 7 times 6 factorial. And that's kind of what this is saying. But what if I wanted to write it as 7 times 6 times 5 factorial? Absolutely. So remember, the factorial means keep going. This is by definition. It sure makes everything work out very well. And when you get into combinations and a number of choices, there is one way to choose 0 objects. So there's kind of a philosophical justification for that. Really important that you feel good about breaking n factorial up. All right. So express in factorial form. Well, I want to say n factorial because but that's n 9 times 8 times 7. You know, where did this go? Well, if we just divide this by 6 factorial, wouldn't that take out the 6, 5, 4, 3, 2, 1? Absolutely. So that's pretty cool. So if I ever ran into 9 times 8 times 7, I could rewrite it as 9 factorial over 6 factorial. And then I could show off to all my friends the little factorial button on my calculator instead of 9 times 8 times 7. Boring. Factorial. Good. All right. A little bit more interesting over here. Certainly I'd probably start out with 11 factorial. Since 7 and below is gone, I put 7 factorial. And then since this is just 4 factorial, I'd put something like that. And this is actually a pretty cool number. It answers a certain question called, how many ways can I choose 7 objects from 11? Or how many ways can I choose 4 objects from 11 objects? Interesting. Wonder why. All right. So sometimes you have to use a little bit of algebra, a little bit of manipulation when it comes to factoring. So I see that there is an 8 factorial in both of these. Maybe I'll just write this first one out so you can see it a little bit better. When you factor out, you're finding the biggest factor that can go into both, and we know 8 factorial is pretty big. If we divide that out, we get 10 times 9. Divide that, we get 1 over this really weird 89. Who would put 89 there? That's so weird. 10 times 90 minus 1, 89. Oh, now I get it. Cool little math book. So that's just a fancy way to write 8 factorial. All right, so what we're much more interested in is something in general like this. So what we have here is, n factorial can be written as n times n minus 1 factorial minus n minus 1 factorial all over n minus 1. So I can factor out an n minus 1 factorial, and I get n minus 1 over n minus 1. That cancels that. And I get n minus 1 factorial. Very cool. So both of these kind of, if you're looking at this, it's always that term, because that's what you do, is you recognize patterns. It isn't, okay? So they just kind of wrote it like that. All right, now we're getting into it. Permutations. Permutation is a group of symbols in any arrangement of those symbols in a definite order. So sometimes we associate and we say order matters or order doesn't matter. I don't even know what that means. So when we say order matters, that means we're counting different orders like A, B, C, and we're counting B, A, C as a different order. So those count separately. So there's 1, there's 2. But the groupings, A, B, and C together, 3 friends hanging out, we don't care about order sometimes. So we say, hey, how many ways can we group it? Different. So permutation today, order matters. We want to count all the different ways we can do it. So I'm going to build a house soon, and I have 8 pieces of artwork that I can choose from. And I have been lucky enough to travel around the world to see most of these paintings. You need to go see them. You need to be in the presence. It's like they say they're great for a reason. You got to go and just let it hit you. Oh my goodness, it's amazing. So I have to pick 3. I don't even know. I'm a big fan of Vermeer. Whoa, why is that? Why? Oh boy. So this is jumping. So I'm going to try to settle it down. I think that works sometimes. So I'm a big fan of Vermeer. Da Vinci Last Supper. Oh my goodness. I believe Sistine Chapel is unbelievable. So I'm going to make that my ceiling. And hey, American Gothic, come on. I mean, we got yeah, I don't know. Maybe, maybe. All right, so there's a lot. Okay, there's a lot. And this problem says, how many ways can I have 8? Well, one way to think about it is, how many choices do I have? How many choices do I have? Well, I have 8 choices for that spot. That would leave me with 7 paintings left to choose from, and then finally 6. So that is a number, but I'm Mr. Fancy Person. I want to write this in terms of factorial notation, so I write this as, but I hope you can see I had 8 choices, 7 choices, 6 choices. All right, just to make sure that you feel good about what a permutation is, I'm not a fan of having you write things out. So next time you see a problem that says, hey, write out all the permutations, and I don't ask you to do it, say, oh, good. 3 permutations, one at a time. So we can do X, Y, Z. 2 at a time just means you're grabbing 2 of those in both orders. So here's X, Y. Here is Y, X. So those are counted separately. Same group of elements, but in different orders. And then obviously there are 6 different ways to mix 3 items, because you get 3 choices for the first place, 2 choices for the second place, and 1 choice left. That would be 6, and there they are. Cool. All right, so in general, when you have, let's say, 5 items to choose from, and you want to take 3, it is important to recognize you have 5 choices, 4 choices, 3 choices, and so in this case it would be 5, 4, 3. Written factorial, that would be 5 factorial over 2 factorial, and interestingly enough, maybe that would be 5 factorial over 5 minus 3 factorial. Yeah. Why would anyone go from here to here? Not a lot of people, unless you're kind of in a math class trying to develop a formula. And then, who would write a 2 in terms of a 5 and a 3? Now, I will bring your attention to what are the 2 interesting numbers in this problem, where there are 5 objects and we are taking 3 of them. So maybe, just maybe, those 2 numbers create a formula that will always work and represent this, and more importantly, represent that. All right, so here is the formula. I'm going to write one more thing, NPR. So N is the number of objects, total number of objects, total objects. And R is kind of like our subset. Whoa. R subset number. So what we do is we take and we find out how many ways, and then excuse me. So I hope you can, man, it's not enough time, but maybe if we had it on the whiteboard and you could see it in different ways, what you're boiling down is you want the number of choices for the first one, second one, and third one. In this case, if we did the 5 and the 3, but we don't want to start and end at random spots. We want a general formula that always works. So this certainly will work out for us. Let's do a few examples. We have 1, 2, 3, 4, 5, 6 P3. So 6 P3 for A. 6 items. How many ways can we arrange 3 of them? So that's going to be 6 factorial over 6 minus 3 factorial. 6 factorial over 3 factorial, and that is 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Those cancel, and look, just what you would have expected if you didn't do all this stuff to get in your way. you have 6 choices, 5 choices, 4 choices. Okay, so this is more the intuitive look, okay, and this is more of the we've got to just rely on the mathematics so that maybe we can use this and do some algebra with it. 120 ways. 120 ways to do that. 1, 2, 3, 4, 5, 6, 7, taking 5 at a time. 7p5, 7 factorial over 7 minus 5 factorial, 7 factorial over 2 factorial, and that, my friends, is a cool number. So we have this cool formula that does some cool stuff for us, but once you start the homework, you're like, wait a minute, this question isn't really asking me what I'm looking for. So this little gremlin. So do not rely on the formula. You've got to think about it, and when the situation calls for it, then use it. And really know that you're finding the number of arrangements of R objects given a choice of n objects. So if we read number 8, how many 3-digit numbers can be formed using the digits? So we get to choose 2, 3, 4, 5. And then we have stipulation. So often as desired. That means 2, 2, 3 could be a number. We can, once we use a number, it doesn't matter. So when we think about it, how many choices do we have for the first one? We have 4 choices because there are 4 numbers. The second one, we have 4 choices again. And the third one, we have 4. There's no formula for that. That's where you just have to kind of think about it to yourself. There are 64 different ways. 64 different ways. Over here at most once, so that means we are choosing 3 out of those 4. 3 out of those 4. So if you did it this way, you could certainly say I have 4 to choose from, 3 to choose from, 2 to choose from. But what I'd really rather you say to the world is I have 4 and I'm kind of picking 3 of those and counting how many arrangements. So that's 4 factorial over 4 minus 3 factorial, which is 4 factorial over 1 factorial, which is 4 factorial, which is 4 times 3 times 2 times 1. It's not going to change it. It's perfect. Awesome. All right, so then we're going to amp it up a little bit. And all I can do now is a bunch of examples. So if you're feeling, hey, I've got this, I don't need, but I don't know. Let's check it out. 3-digit numbers made up using 0 through 7. So there are 8 total numbers to choose from. So I kind of make myself a little note. Most one each. The number cannot start with 0. So 0 cannot go in the front. How many different numbers can be found if there are no restrictions? Well, if 0 can't go here, how many choices do I have? Well, I have 1, 2, 3, 4, 5, 6, 7. So I do have 7 choices. Okay, that leaves me with 7 numbers, including the 0. So now, this is A. So now I have to pick 2 of those numbers out of that 7. So it's pretty easy to just write 7 times 6. I have 7 to choose from because I can't choose a 0. The second number, I have 7 numbers left to choose from, and then obviously I have 6. So this is right. I think you get 394. That's totally right. Another way to write it that's a little bit more mathematical is going to be 7p2. There are 7 objects left. I'm going to pick 2 of them. So, and then when you plug that in, you get 7 factorial over 5 factorial, 7 minus 2, and that's 7 times 6. So try to, don't get caught just trying to multiply these numbers out. Try and use this formula more and more. All right, let's look at B. The number must end in 2, 4, or 6. So how many choices do I have if this has to be a 2, 4, or 6? Well, there's 3 choices. 3 choices. So my number of, once I've picked that, whatever, 2, 4, or 6, that leaves me with 7 numbers remaining. 7 numbers remaining. But one of them is a 0. So I really only have 6 choices for that first one. And now, how many numbers do I have left for this middle one? I have 6 left because now 0's back in there. I can do that. And man, I can't remember. 36108, I think, is the number of that. C. The number must end with a 0. So that has to be a 0. So that's picked. So there's only one choice there. Go ahead and put a 1 there if you want. Well, I have 7 more numbers. I have no more restrictions. I don't have to worry about this being a 0. So I could write 7 choices there and 6 choices there. And I get 42. That's cool. I could kind of write this as 7, 2. And if I plug that in my calculator, I get 42 also. Hey, part D is pretty cool. Must be even. Well, what is an even number? It means it's 0, 2, 4, or 6. I want you to know that we have this problem done already because here we found the number of ways to get 2, 4, or 6. And here we got the number to get a 0. And what I really want to bring to your attention is those are 2 different cases. Because that 0, where the 0 is, can we pull it or not? So if I only had to do problem D, I would still have to break it up into 2 cases. So just take a deep breath. When things are like, well, if this is it, then that changes this. That means it's probably look at those 2 separate things. So we're going to get 150 for that. This plus that. Awesome. All right, 10 students sit in a row of 10 chairs. How many ways can this be done if there are no restrictions? Well, 10 factorial. 10 factorial. Okay, big number, 3 million something. All right, part B, very important problem, huge. A, B, and C, we're the trifecta group. We have to sit together. So they kind of take up these 3 chairs, or these 3 chairs, or these 3 chairs, or these 3 chairs. So what we do is we combine them as one item. We combine them as one item. So I'll do that like this. And think of that spot they take as now we don't have to worry about, we have less things to worry about. So we're going to take these away. So maybe. Now we had 10 chairs, now we have 8. 1, 2, 3, 4, 5, 6, 7, 8. What we're going to do here is we're going to treat A, B, and C as one item. One item, okay? So that leaves us with basically 8 students, right? So there are 8 factorial ways to arrange those 8 students. But one of these students is this set of 3. So that's pretty cool. Now we have to count how many ways can those 3 students be arranged, because it could be ABC, BAC, CAB. So that is 3 factorial. This is a key problem. When things are grouped, group them and consider them as one object, and then do the problem just like you would, and then multiply it by how many ways we can arrange those objects together. All right, I grew up in Minnesota till 3rd grade. Therefore, I have an amazing hockey skills. First word you learn to spell in Minnesota is Mississippi, because we got the Mississippi headwaters. MISSISSIPPI, something like that. We used to do it all fast and cool. Well, let's count how many ways we can rearrange those. So there's 1. There's 1. There's 2, because obviously I've flipped a few I's. There's 3. Man, this could take forever, isn't it? Well, the first thing I would like to bring to your attention is, yes, I flipped some letters around, but they are still the same arrangement. Unless those I's have some weird difference between them, like different fonts or something weird that makes them different characters, they are considered the same, and therefore all three of these are considered the same arrangement. So when you count the number of ways something can be arranged and there are multiples, let me just give you the answer to this, and then hopefully the formula will make sense. There are 11 letters in Mississippi, I think. 1, 2, yeah, 11. So there are 11 factorial ways to rearrange those letters. Awesome, awesome. Now what we do is just look at the eyes. How many different ways could I do the black, green, red, and blue eyes? Well, there's 4 of them. So there are 4 factorial ways for just me taking care of the eyes. Well, there's 4 S's. So we need to divide out how many ways we could rearrange the S's, and there are 2 P's. So the number of arrangements of this particular set of letters is just the total number of letters divided by these multiple things. This is the way the book gives you the formula. You have to really read it. Suppose there are n sub 1 of the first symbol. So the n sub 1 is the number of repetitions that they have. So if you can see in the top, they're all added. So that basically is covering how many letters we have. For our example, it would be n. Oh, seriously, it jumps down that way too? Wow. N1, let's say, is M. That's 1. I, N2 would be 4. S would be N3, and that would be 4. And P, N4 would be 2. So there's your 11. That goes on top, and then divide by 1 factorial, 4 factorial, 4 factorial, 2 factorial. That is not a formula to memorize. The process is what you should need to memorize. All right. I know I'm getting up there, but yep. 1 red, 2 white, 3 blue are placed in a line. How many distinguishable ways can this be done? With the white marbles at each end. So what's happening here is now they're just forcing you. It's like saying that it has to end with a 0. So don't freak out. Just make the problem easier. So if the outsides have to be the white marbles, then all you're counting is how many ways can you arrange the marbles that are left. So in A here, the white marbles at each end, they're kind of out of the picture. So now we have 4 marbles left, but we have to divide out any multiples, and that's going to be 3 factorial. So that is actually 4. There are only 4 ways to arrange those 6 marbles so that the white ones are at the end. All right, I'm going to let you finish that one. I got much more interesting ones to deal with. Do I want to do this one? Let's skip it. All right, we're going to do a tough one. So this is number 19. Alice's book, 10 adjacent front row seats for a basketball game. Awesome. Alice, I wish I was hanging out with you, buying tickets for your friends. How many different arrangements are possible if there are no restrictions? Well, if you got 10 people, 10 ways for that arrangement, that's a slam dunk. That's 10 factorial. Done. We are done. Okay. Uh-oh, it snowed. Dang it. So unfortunately, 4 of the friends couldn't make it. Dang. Stupid front wheel drive, old car, whatever. But they're okay. They're okay. Everybody's safe. So how many ways can we do? So now we're asking how we've got Alice. That's Alice. And we've got 5 of friends. So we have 6 people. We have 6 people. So this is pretty cool. No restrictions. So how many seats could Alice choose from? Well, she has 10 to choose from. Then the next person has 9, 8, 7, 6, 5. Huh? Huh? Not too bad. Not too bad. So it's all about choices. It's all about choices. and that's a number. I don't know what it is, but do you see how I didn't put the 10, 9 on the seats? Because it wasn't about where the, you know, how many choices does the seat have? It's really how many choices does the person have. Let's try another one. Part B2, they all sit together with no empty seats between them. Ho, ho, ho. All right. Whoa, 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 whoa. Careful. So what we have there, Control G, that means they sit here, 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 they sit here. All right, so that's kind of, sometimes you don't have one of these cool things to help you, but that's the idea. So first of all, how many ways can we arrange the 6 of them? So that's going to be 6 factorial. And then how many options do they have where the 6 of them can sit together? Well, there are 5. So they can be there. There's 1. There's 2, 3, 4, 5. Sure looks like 6. Why do I have 5? 1. Oh, because I didn't make this big enough. There's 6 of them. There's 6 of them. I know you caught that. Sorry. We don't have that much time. There we go. So there are 6 people. There's 1. There's 2, 3, 4, 5. All right. And that's a number. Cool. Hey, last one. This is messed up. It took me a little bit. Any 2 of Alice's friends sit beside her. So what do we know? We know Allison has to sit here because she's got her friends on both. So 1, 2, 3, 4, 5, 6, 7, 8. So there's really only 8 choices for her. So then she's going to have 2 friends beside her all time. Boy, she's got to have that person right next to her. So how many ways can we pick 2 of them? Oh, now we're starting to trust the math. There are 5 people left. And 5p2 would represent the number of ways for us to pick 2 of those in any order. So let's say 2 are now gone. That leaving, now we have 3 to deal with. We have 3 left. Is there any stipulation where those 3 sit? No. We have taken up 3 seats. Therefore, there are 7 seats left. So there are 7p3 ways for those 3 remaining people to sit in those 7 remaining seats. So our final answer is 8, 5p2, 7p3. Awesome. And that's a number. 8 times 5 times 4 times 7 times 6 times 5. And it's a pretty cool number. Woo! All right, I know, 33 minutes. It's going to be kind of a 2-day lesson, so if you don't get all the way through it, we only have one more section, and so we'll spend a lot of time on that. Thank you.